So very good afternoon to everyone. So I'm Rohit Garg and I will be taking the week 11's material characterization detailed course. So in the last day we talked about basics of the TAM and from the TAM diffraction what can be inferred. So we were discussing about that in detail. So we discussed that phases and crystal structure types, crystal symmetry and space groups, orientation relationship between phases, determining growth direction, interface coherency, defects identification, example, twins, dislocations, ordering behavior of crystal structure and the site occupancy preferences. These are the things that can be determined from the TM diffraction. So now the question comes, why the electrons only? So anyone would like to answer that? So the ability to resolve the tiny objects improves as the wavelength reduces. We already know that from the week 1 class, week 1 lecture. So let us consider the microscope objective. Okay, so these are the objects to be resolved. So distance between the D, and then this is the focal length of the lens. If image plane is at a large distance, and then so then we determined that the critical angle for resolution is given by 1.22 times lambda by D. So the minimum D for which we can still resolve two objects is AC times the focal length. Okay, so D minimum is approximately F alpha AC. Then it can be written as 1.22 lambda F by D. So a good microscope objective has F by D is around 2. So with lambda around 500 nanometer, the optical microscope has a resolution of around 1 micrometer. Okay. So let's continuing on that. So the resolution of the electron microscope. So firstly, you know that it behaves as light as well as matter. So behaving like light, it can be as h by lambda. Matter also it can be written as. So and P is E by capital E by C. Then energy can be given as hc by lambda. And for if we consider it as a matter, then energy can be written as h square by 2m lambda square. So the for the wave behaviors, images and diffraction patterns, wavelength can be termed by energies. And for the charged particle behavior, strong electron specimen interaction, then the chemical analysis is possible. Okay. So like typically electron beam current in TEM is around 0.1 to 1 microampere, which corresponds to 10 to the power 12 electrons passing through the specimen plane. So with around 100 kilo electron volt energy, these electrons travel at about 0.5 C, approximately 1.6 times 10 to the power 8. So they are separated by 0.16 centimeter. This means that there is never more than one electron in the specimen at any one time. And further, the electron diffraction and interference occur, both of which are wave phenomena and imply interaction between the different electron beams. Now for the fundamental constant and definition, we talk more about the electrons. So the charge is given by 1.6 times 10 to the power minus 19. 1 electron volt is around 1.602 times 10 to the power minus 19 joule. So the rest mass is around 9.1 and 10 to the minus 31. Then the rest energy can be calculated and followed by the kinetic energy. The Planck's constant we know in 1 ampere. So the speed of light in vacuum is around this. Okay. So the de Broglie wavelength of an electron can be given as lambda is h by p, and then the relation between the electron's wavelength and its kinetic energy E. So P and E are related through the classical formula, we know that. So E is given by P square by 2m, where Me is 9.11 times 10 to the minus 31 kg, and energy can be given as h square by 2m lambda square. So h is uh, 4.14 times 10 to the minus 15 electron volt second, and we can calculate E as 1.505 eV nanometer square by lambda square. So don't confuse this with for energy of photons, which is given by 1240 eV by lambda, and for electrons it is given by 1.505 eV nanometer square by lambda square. So let's solve an example. So we wish to observe a virus with a diameter of 20 nanometer, which is much too small to observe with an optical microscope. So calculate the voltage required to produce an electron de Broglie wavelength suitable for studying this virus with a resolution of d medium around 2 nanometer. The F number for an electron microscope is quite large, so F by D is around 100. So try to solve this and we will discuss about. So we can solve it by D minimum is 1.22 times lambda F by D, and then we can so we find out that the lambda is around 0.0164 nanometer, and similarly we can we can calculate energy as 5.6 kilo electron volt. So that means to accelerate an electron to an energy of 5.6 kilo electron volt requires around 5.6 kilovolts. Now there is one more thing like I want to cover. So we discussed briefly about the SAED pattern in the last class. So we will discuss about indexing SAED patterns. So firstly, we select the central spot. After selecting the central spot, we measure the distance between central spot and other nearest spots. This gives the So this is the inverse of the d spacing, 1 by d for a particular HKL. Now take the ratio of the distance measured. Compare the measured ratio with the expected from the table 1 given below. Now start giving the indexes for matching ratios as given in the table. Now cross-checking the indexing by measuring the angle between vectors joining the central spot and the other spots using the following equation. Now find the zone axis using any of the two indexed HKL, and then make sure that all the indexed HKL satisfy the zone law. Okay. So here I summarized for in table for all the details for you. So like these are the some examples, simplified examples for you. So pattern 1, pattern 2, pattern 3 and pattern 4, and then these others. So you can all try these and you can discuss. So very good afternoon to everyone. So I am Rohit Gehlot and I will be taking the week 7's materials characterization problem solving session. So in the week 7, majorly the uh, things which were taught were about the X-rays, their source, generation and all. So I will be so as already like in the yesterday's week session, like a lot of problems are already been discussed. So majorly I will be covering the theory part, and in the subsequent lectures coming the next week, we will be discussing more and we'll go deeper in the problems also, and also we'll be discussing some real life experiences and real life problem solving sessions on the X-rays. So if you talk about the X-rays, like the first question is like how to probe structure of the materials. So any kind of structure, like any kind of crystallographic information, like or lattice parameters or atomic positions, how we can determine for a particular material. So we can say like X-rays are the agent for this. Like with the help of X-rays, we can determine the crystallographic information like lattice parameters and atomic positions and many more other details. So X-rays are very important nowadays. XRD is very important tool for this. So in this diagram, as it can be seen, there is an X-ray tube which is a source of the X-ray generation, and from this the X-rays are falling on a sample. This sample can be a metallic sample or a powder sample or some polymeric sample also, and then the response of this is detected by a particular detector, and then this is shown in your like output or in your computer. So there you can see, if you see like this is the diagram of the simple XRD with a protective shielding emitter. So this is your X-ray tube and your shield, and this is your sample holder, and here is the divergence slit, and this is your counter and pre-amplifier, and then the detector, and here we place the sample. So the first thing is that your why X-rays are so much popular now these days, and what are the basic properties of the X-rays. So we see that X-rays are much more penetrating than the light because they have higher energy, and also like they easily pass through the human body. That is what you can see here. That is why the X-rays are very much used in the radiography also. So by placing a source of X-ray on like for this type of image, like we place source of the X-ray on one side of the object and photographic film on the other radiograph. So by this way we can see like the details of if any human fracture and some kind of tensile stress defects and all. So the major thing is that the less denser of portion of your object allow a greater portion of your X-rays to pass through than the more denser. So that's why we can see the X-rays were first detected by or discovered by the Röntgen in 1895. He got a Nobel Prize in the physics on 1901 for this. X-rays have so X-rays are like the electromagnetic radiations of exactly the same nature as light, but it has much comparatively shorter wavelength, and the wavelength of the X-ray is in the range of around zero point 0.5 to 2.5 angstrom. Like, but for the visible, it was around 6,000 angstrom. Okay. So the three things that are important is first one is that these are the electromagnetic radiations, and these affect the photographic films, and their wavelength is much lesser than the visible light, and X-rays penetrate more compared to your visible light. Therefore, they are used for detecting uh, bone failure and other details. So, so so how the X-rays are produced. So firstly, this is the schematic cross section of an X-ray tube. So here, like it comprises beryllium window, tungsten filament, and glass. So this is your tungsten filament. So firstly, the current is passed through the filament or your cathode. Generally, it is used tungsten. So due to this current, due to the current passing, the heating of your filament happens, and when this overcomes the work function of the material, then the loosely bound electrons or the outermost cell electrons starts to emit, and as you can see, like these electrons are emitting, and then they maintain a potential difference once between the cathode and the anode of around 10 to 30 kilovolts. So there is like when the potential difference between your cathode and the anode is around 10 to 30 kV, then these electrons start to draw out from the cathode towards the anode, and then further these electrons will hit your target. This is your target, and then start to deaccelerate. And why they start to deaccelerate and what happens in that, like we will be discussing in the later section. So after that, these start to emit your electromagnetic waves, okay, and due to which the X-rays are generated. So we maintain a proper vacuum system in the X-ray tube, and the Beryllium window at the top allows the X-rays to come out of the tube. So this is the Beryllium window. From here and here, your X-rays starts to come out of the and then it's like sequentially collimated and to fall on your sample. I hope this is clear. So once your X-rays are generated, the rays coming out from your target, like it consists of a mixture of different wavelength and with varying intensity, and further this lambda is highly dependent on your tube voltage. You know this. So the tube voltage for which the tungsten filament was working on. Your intensity is so from this, like you get the plot like this. So as written here, as I have written here, X-rays of multiple wavelength come out of your beryllium window, and then there is a term known as lambda SWL, which is a short wavelength limit. So we can define it as like I can say, so the electrons which are like stopped in your one impact, as the electrons fall on your target, and which are completely, like a series of things can happen, like some lose their energy partially, some lose their energy completely, and the electrons which lost their energy completely and stopped in the impact will give rise to the photons of the maximum energy, photons of the maximum energy, which means like the rays of minimum wavelength. So these are the points where the rays of the minimum wavelength are present. So at that, when your at this point, your minimum wavelength is defined as we can write it as C by nu, and then we can write it in terms of Planck's constant, and then hc by E nu, where what I have written, nu is equal to, and then your intensity. Okay, so there are three things, like three curves, A, B, and C. Okay, so these are the electrons coming to rest at a plural scattering or so as seen here, like A, B, and C. So the electrons coming to the rest after multiple scattering, okay, or deacceleration. Then this is the lambda SWL. So after single impact, here what I have written, like here, after single impact, if the electrons coming to completely rest, then it can be written, this condition can be defined as E nu is equal to H nu. EV is the energy of your electrons, and then when it completely comes, then it converts to photons of the maximum energy. So I written at H nu. So from here we can define your lambda SWL as this. And one more thing is that your current at these L lambda SWL, your current is 0 up to a certain wavelength also. At those current at those lambda where current is 0, it's called your SWL, and then it increases rapidly to maximum and decreases afterwards with no sharp limit on your long wavelength side. Okay. Now one more thing comes here, that what are the parameters on which your lambda SWL depends. Okay, so we can say that as your tube voltage increases, your intensity of the wavelength increases, and both SWL, that is your lambda SWL, and position of the maximum shift, like the position of your maximum shift to your to shorter wavelength. So therefore, as your applied voltage will increase, the number of photons per second emitted will increase, and your average energy per photon will increase. Okay, so keep this point in mind. And the total energy or total X-ray energy emitted per second is your proportional to the area under like these curves, area under one of these curves. The area under one of these curves will define the total X-ray energy emitted per second. Okay, and another parameter will be the atomic number on which the target on the target which it is falling, and the third one is a tube current. So therefore, this depends upon these parameters. A, this is a constant, then Z is your atomic number, and then your voltage, and A and to the power m. This is the constant. Generally, it is 2, around 2 or around 2. So like if we move to this, so continuous spectrum is caused by your rapid deceleration of electrons by the target, and then the origin of your characteristic spectrum lies in the atoms of the target material itself. Okay, so this is the characteristic. These are the characteristics X-rays. Okay. These are your characteristic X-ray. So in the characteristic X-ray, like as I told us that these are the continuous spectrum is caused by a rapid deceleration of the electron, right? So if one of the electrons bombarding your target, like if it has sufficient kinetic energy, like it can knock an electron out of the K cell, right? And then due to this leaving of the atoms in a higher energy state, like one of your outer electrons immediately falls into the vacancy of the K cell that was created by due to the impact, and due to this the characteristic X-rays are formed. So there are majorly three things are considered: K alpha 1, K alpha 2, and your K beta. Okay, so this is how your origin of the characteristic spectrum takes place. So the incoming electrons is knocking off an K cell electrons. Okay, so this is the incident beam. Due to this, the K cell electrons were emitted, and then the L cell electrons moves to your K cell vacancy. Then due to this, the K alpha 1 generates. So if here it is written that if it moves from L cell to K cell, then K alpha 1 will be generated. If it moves from M cell to K cell, then K beta will be generated. And if it moves from K cell to L cell, then L alpha will be generated. So here I've written that K alpha 1, K beta, and then L to K, smaller quantum jump, right? From L to K there is a smaller quantum jump. However, from M to K there is a larger quantum jump. Okay, so therefore the K alpha 1 will be have a higher intensity compared to K beta. Okay, but however the K beta has higher energy than K alpha 1. Okay, sorry, so yeah, K beta has a higher energy than K alpha. So so the thing is that your so if till now if anyone has any doubt, we can discuss. Okay, so now comes the Moseley law. So the Moseley law equation is given by this: root of V is equal to C multiplying by Z minus alpha. So the wavelength of any particular line decreases as the atomic number of your emitter is increased from this relation. So this is the relation between mu. So from here also it can be seen that so as your atomic number is increasing, the wavelength of your any particular line like K alpha 1 or L alpha 1 is decreasing, okay, as your atomic number is increasing. Okay. Okay, so this is your wavelength. So it is like that as you move from left to right, it is decreasing. However, your atomic number is increasing as you move up. Okay. So the wavelength of your any particular line, like whether it is K alpha 1, L alpha 1, or K alpha 2, will reduce as the atomic number of your emitter is increased. There is a linear relation between the square root of your line frequency mu and the atomic number Z. For copper, your lambda is around 1.5406. This is generally used in your X-rays. Okay. So now, if we see the interaction of your X-ray with your matter, with your target, then generally the absorption is the major phenomena. So as you can see, like this is your target material of particular thickness X. So as the X-ray falls of your intensity I0, and then it comes out as IX intensity. So some of the intensity it has absorbed. Okay. So 1 second now. Okay. So this is your fundamental of your absorption. This slide shows. So this is your incident photon. Okay, and these are your particular KLM cells. Okay. And then as like it is striking the incident photon, so this is your photoelectrons. Okay. Then your auger electrons are these, like due to this the energy difference, if some electrons removed, then your auger electrons are generated. While if the X-ray is that this is striking your K cell, if your K cell electron is removed, and then your upper some lower energy like cells go to this, and electrons move from this to this, then your X-rays are generated. Okay. So rule of the nickel filter. So generally for your analysis we want to have separation of your K alpha and K beta. So generally nickel filter is utilized, so it bypasses the K beta. So we are able to get K alpha, but still it is a problem like K alpha 1 and K alpha 2 separation. So continuous and characteristic X-ray. So for the characteristics X-ray, it can be written as a function of your Bi, V minus Vk to the power m. V and m are constants, and V is your potential difference between your filament and the target material. Okay, and this K is your excitation voltage, and then this I is your tube current. However, for the continuous spectrum, it is given by A, I, Z, V to the power m, where A and m are constants. V is your potential difference between filament and the target material. I is your tube current, and Z is your atomic number of the target. Okay, so the two the relation between your continuous and the characteristic X-ray is used with these two equations. Okay, so the characteristic X-ray depends on your tube current, potential difference between your filament and the target material, and your excitation voltage. Okay, however the continuous spectrum depends on your tube current, which is same as the characteristics, atomic number of the target, which was not in your characteristics X-ray. Okay, So here like this is like 10 kV, this is 20, this is 25, this is 30. So as it is increasing, then your K alpha and K beta are generating. Okay, so K beta can be removed by your nickel filter, and then uh, your characteristic X-ray, this one. Okay, these are your continuous spectrum. The continuous spectrum depends on your tube current, voltage, and your atomic number. Potential difference between your filament, and this depends on an additional excitation voltage, KL, excitation voltage of that particular material. Okay, so this is how the interaction or your absorption is like determined. So we can, the rate of change of your current is a function of your linear absorption coefficient of the particular material. It depends on your material to material, it may vary. So therefore we can derive the current in terms of your linear absorption coefficient as Ix is your I0 the e to the power minus mu x, and then your Ix is I0 e to the power minus if we write it in mass absorption coefficient, then nu by rho to the, then x we can also write in terms of rho, then it is rho time dx. Okay, so for steel it is around 7.8, and for magnesium it is around 1.8 gram per cc. Then we can write nu by rho average can be written as a summation of W1 mu by rho 1 plus W. If your material is non-homogeneous, then your nu by rho will be like this, by can be written by this. So now there are like soft X-rays and hard X-rays. Okay, so nu by rho is your function of your lambda cube to the, and the atomic number. Okay, so these, the more details can be like elements of X-ray diffraction by B.D. Khalid in their book. More details are given. Then if you further move to the fundamentals of absorption and the scattering of the X-ray by atoms. So like suppose for the lambda is around 2.5 angstrom, then it can be written, or then it can be written as mu by rho is around 180 centimeter cube by gram. For lambda is 1.48 unusual behavior source, and then so this is the plot between that mu by rho and your lambda. Okay, so this your AB and CD is your unusual pattern. Okay, and then at lambda is around 1.48 unusual pattern, unusual behavior is there. So lambda around 1.48 exactly matches the K cell excitation energy of your number atom of the nickel atom. Then the energy of your X-ray around 1.48 at 1.48 angstrom is getting transferred as your kinetic energy of the ejected electrons. Okay, so now the role of the nickel filter. So if your target is copper, then nickel filter is utilized. If your target is cobalt, then iron filter is utilized. If your target is chromium, then vanadium filter is utilized. And if your target is iron, then manganese filter is utilized. So depending upon the type of target, your filter may also change. Okay, so this is how the role of the filter is determined. It reduces the intensity of the K beta to minimalistic level. Okay, but still in the background it comes, I will show in the last slide. So X-ray are the electromagnetic waves with a dual nature, and for the crystals with a long range periodic arrangement of atoms. The crystals are made up of the long range periodic arrangement of atoms, and of X-rays are electromagnetic waves with wavelength of angstrom region. Then crystals will act as a 3D diffraction grating for the X-rays. Okay, so this is your like, these are your crystals. So crystal with a long range periodic arrangement of, crystal is generally defined as the long range periodic arrangement of atoms. Okay, so if your crystal are made up of long range periodic arrangement of atoms, and X-rays are electronic wavelengths with a wavelength lambda, then these crystals will act as a 3D diffraction grating for the X-rays. Okay, so now if we define the Bragg's law, which is very important now. So we all know that n lambda is 2d sine theta. So if the wave is defined in a plane wavefront, parallel wavefront, then these two wavefronts are coming 1 and 2, and then the second one has to travel this additional path difference ml plus ln, and then this additional path difference can be defined as your 2d sine theta, that this one ml plus ln. So ml can be given as your d sine theta, and ln can also be like d sine theta. So this path difference is 2d sine theta. Okay, and then d is your HKL. This is difference between distance between your like these are atoms. Okay, so n lambda is 2d sine theta. And from here we can write it in terms of lambda as 2d HKL by n sine theta. So now if we see more deeper in your Bragg's law, so Bragg's law considered crystals to be made up of parallel planes of atoms. So, okay, so these are the parallel planes of your atoms. And then the incident beams are reflected. These are your incident beams are reflected specularly from these parallel planes of atoms in the crystal, with each plane reflecting only a very small fraction of the radiation. Okay, so, and then these E, F, and DE can be written in terms of D is a planar distance between. Then it can be written as 2D sine theta. So n lambda will be 2D sine theta. So the constructive interference of the radiation from successive planes occurs when the path difference is an integral number of wavelength. This is the Bragg's law. Okay. So then further, if the path difference between these two the same order, then your constructive interference happens, and then a higher intensity radiation will be seen. However, the others can, like destructive interference, can also be seen. And then this Bragg's law applies to all sets of crystal planes. The lattice can be deduced from the diffraction pattern, making use of general expression for the spacing of the parallels in the Miller indices. So for cubic structure, D is given by 8 divided by root h square plus k square plus l square. So for different crystal structures, the formulas are different. We all read in previous classes. So this is the simple XRD pattern like what we see from the output. In the further classes, we will be discussing about the pattern, whether it is BCC, FCC, or some other kind, or mixture of all these. So, and how to identify materials also. So this is what happens. Like this is your strong intensity of prominent crystal peak planes. Okay, so these are your higher the intensity, like stronger your intensity, then it says that your prominent crystal plane is that. Okay, and these are with a lower intensity. So these are your subordinate crystal planes, like they are present, but the prominent crystal plane is this. This is what from the XRD peaks intensity we can find out. And then this is the background radiation. It can be subtracted during analysis. So from after analyzing these, we get that your D spacing, like for around 2.88 D spacing, we are getting the intensity maximum around 100, and for 2.18 around 46, and so on. Okay. So, and one more thing that here, like what I discussed, that generally the K alpha 1 is higher, like, right? So it is like the more probable that your K cell vacancy will be filled by your L cell, right? But it is nearer here. K cell vacancy will be filled by your L cell electron. Okay. Then the N cell, because then it has to travel more, right? So therefore the K alpha line is stronger than your K beta line. Okay. And yeah, more or less, yeah. So if anyone has any doubt till now, we can discuss. Okay.